Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper from the Hugging Face trending list, published on February 24th, 2026, just 2 days ago. It addresses the massive storage costs of late interaction retrieval systems by introducing a new method called attention-guided clustering, which compresses document indices into a fixed budget while retaining about 97% of the original performance. The paper is titled Multi-Vector Index Compression in Any Modality. And as we'll see later, the results on video retrieval are particularly striking, with the compressed model actually outperforming the full version in some cases. And for those interested in the implementation, the authors have shared their code on GitHub. Figure 1 immediately highlights the main efficiency gains reported in the paper. The top bar chart compares the proposed method, attention-guided clustering, against 3 baselines. The pink bar demonstrates that it retains over 97% of the original model's performance, significantly outscoring alternative approaches like sequence resizing. Moving to the bottom plots, we see why this compression is feasible. On the left, the full uncompressed index shows that most vectors in a standard model are barely used, whereas the right panel illustrates how attention-guided clustering condenses that sparse signal into a compact, fully utilized representation. Alright, Figure 2 breaks down the specific compression techniques the authors explored. The top diagram outlines the shared workflow. Multimodal inputs pass through an encoder, get compressed into a fixed set of tokens, and are then stored for retrieval. The bottom section details the 4 strategies, starting with Panel A, their novel attention-guided clustering. Here, learnable universal query tokens scan the document to identify key regions, using these as anchors to cluster and aggregate the remaining data. Panel B shows memory tokens, or memtalk, which appends learnable tokens to the input that absorb the context. Panel C depicts sequence resizing, which projects the sequence length down using a simple neural network layer. Finally, Panel D shows hierarchical pooling, where similar vectors are iteratively merged until the token budget is met. So, Table 1 details the performance across text, visual documents, and video retrieval benchmarks. The rows list the different compression techniques with the author's attention-guided clustering at the very bottom. What stands out immediately is the MSRVTT column. Here, the compressed model actually scores higher than the full uncompressed baseline, reaching over 102% of the baseline's recall. This confirms that compression effectively denoises redundant video data. Finally, on the far right, under Multivent 2.0, the baseline entries are blank because the uncompressed index was too large to compute, while the compressed versions handled the scale easily. Well, Table 4 now zooms in on those surprising video retrieval results using the MSR versus TT benchmark. The top section establishes that the uncompressed baseline needs over 1,300 tokens to reach a recall at one of about 56%. Yet, if we look at the middle block for a 32-token budget, attention-guided clustering achieves nearly 57%. It outperforms the full index by focusing on the most relevant signals, proving that compression can actually improve accuracy by reducing noise. Alright, Figure 3 visualizes why the full index is inefficient compared to the compressed version. In the second column, labeled Full, the top bar chart shows a massive spike at the start, meaning the model ignores most of the video data. Contrast that with the fourth column, showing attention-guided clustering. Here, the matching strength is evenly distributed across all 32 tokens, so every vector actively contributes. Finally, the bottom heat maps show that while sequence resizing on the left creates chaotic negative correlations, the AGC method maintains a stable, coherent structure. So, while Figure 3 showed the qualitative difference, Table 9 now quantifies exactly which parts of the attention-guided clustering method matter most. The top row sets the baseline, with the full model achieving a recall at one of nearly 57% on the MSR versus TT dataset. As we move down the rows, we see performance drop when components are removed. Removing attention weights or selection hurts, but the bottom row reveals the biggest impact. Without the clustering mechanism, the score falls to just under 53%, confirming that grouping redundant tokens is the most critical step. Wrapping up, the key takeaway is that attention-guided clustering enables fixed budget compression across text, images, and video without sacrificing performance. By effectively filtering noise, it achieves state-of-the-art results on video benchmarks and makes large-scale multimodal search feasible where storage costs were previously prohibitive. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.